Hello and welcome to the online classes. In this video, let us discuss about the biocoordination chemistry. It is the coordination chemistry of the transition elements that are present at the biological level. So before getting into the core topic, we know that there are 118 elements in the modern periodic table, out of which nearly 30 elements make up the living organisms. Out of these 30 elements, we can classify them into non-metals and metals. Depending on the concentration of these non-metals and metals, we can further classify them into macro and micro in the case of non-metals, macro, trace and ultra trace in the case of metals. When it comes to the macro non-metals, we have some examples such as carbon, hydrogen, oxygen, nitrogen that form the major part of the living organisms, especially the human beings, along with phosphorus, sulfur and chlorine. In micro non-metals, we have boron, very rarely found in some living organisms, silicon, selenium, fluorine and iodine. When it comes to the micrometals, sodium, potassium, calcium and magnesium in their ionic states, trace, iron, copper and zinc. In ultra trace, we have vanadium, chromium, manganese, cobalt, nickel, molybdenum, along with some amount of lead, arsenic, tin and cadmium, which mainly enter as some impurities. Well, now question arises. When it comes to the elements that are completely present, non-metals are also important, but our topic purpose, so let us only restrict ourselves to the metals. Now, in the living organisms, there are several elements. We are concentrating on these metals. So if at all we choose some biomolecules at their active site, we find these transition elements to be present. So those sodium, potassium, calcium and magnesium are also metals, but our topic is restricted to the transition elements. So when it comes to the transition elements, why these transition elements are chosen at the active site of the various biomolecules? To explain this, we have three important features that are associated with these transition elements. The first one being the variable oxidation states. For example, if I choose magnesium, which is not a transition element, its oxidation state is fixed as 2+. But if at all we choose a transition element, a typical transition element, it can be stable in more than one oxidation states. Let me choose the simplest of the examples, iron. Iron is stable in 2+ oxidation state. It is also stable in 3+ oxidation state. So these transition elements, most of these transition elements can switch on the oxidation states, which is an important feature to be present as an active site. Well, coming to the next point, these transition elements also have variable coordination number. So these transition elements can shift their coordination numbers. Suppose if a metal is present in the coordination number of 4, when another ligand approaches, it can increase its coordination number to 5, or it can also increase its coordination number to 6. The reverse is also possible. From 6 it may lose some ligands, can drop to 5, or even it may drop to 4. So a transition element can have a different coordination number. It can also have a different coordination geometry. What does this coordination geometry mean? Suppose if I am taking an example of a coordination number 4. For coordination number 4, the feasible geometries are tetrahedra and square planar. So along with this pure tetrahedral geometry and pure square planar geometry, depending upon the energy considerations, we can also have a distorted tetrahedral geometry. What we see here is coordination number is 4, but coordination geometry can shift from tetrahedra to square plane, which may pass through an intermittent distorted tetrahedral geometry. So this is how the transition metals take up the active sites, by which can shift their oxidation states, which can switch on their coordination number, and which can also switch on their coordination geometry. Now, coming to the criteria for essential elements. Well, we have several elements, but only some elements are called as essential elements. Some other elements are called as non-essential elements. What exactly are essential elements? Now, Suppose if I choose some different living organisms, tissues of different living organisms, when there is a comparable concentration of a chosen element in the tissues of different organisms, such elements we generally call it as essential elements. So element, if it is present in the tissues of different organisms at comparable concentration, we may call it as an essential element. This is one point. Another point is, well, suppose if I choose a living organism, from this living organism imagine that I am having an element which has been withdrawn. Once such an element has been withdrawn, now this living organism will experience some physiological abnormality regardless of the species, whatever be the species. If at all you are trying to withdraw that particular element, that particular organism will experience some physiological abnormality. Then definitely we can say that this element is an essential element. So if it is an essential element, then if I provide the same element to it in the required amount of quantity, then whatever physiological deficiency that arose will be completely removed. So there is a remedy of this physiological abnormality and the deficiency is checked. Such an element we can call it as a essential element. Now coming to the physiological effects of metal concentrations, we said some physiological effect may occur due to the presence of the metal, but when I choose this metal at different concentrations, what are the physiological effects? We'll see it as a graph. Here we can show physiological effect versus the metal ion concentration. We have taken 5 different points, starting from the lowest concentration to the highest concentration. The first concentration is called as the concentration for survival. It is that minimum concentration of the metal ion which is required for the survival of a living being. Suppose if I choose some living organism, that living organism has to survive. So for its survival, it requires a minimum concentration of a metal ion. Such a concentration, we call it as a concentration for survival. Now as the metal ion concentration increases to some extent, then that is a concentration which is required for survival, but there will be some physiological abnormality. Such a concentration we refer as a deficiency. So what is deficiency means? It is a concentration where a living organism can survive, but it will suffer from abnormalities. Then as the metal ion concentration increases to some extent, then we call it as a optimal concentration. So this is the concentration which is required for the proper functioning of all the biological activities. We call it as a optimal concentration. If the metal ion concentration still increases, this is a little bit dangerous to the living organism, so we say that it is becoming toxic because it will severely affect the metabolic activities. If the metal ion concentration still increases, then this concentration will completely impair the physiology, and it will also impair the organisms. It will also impair the organs, and finally the organism may also die. Right. Now after the physiology, another important point is principles for biological selection of the elements. Suppose if the nature is choosing a particular element, why is it choosing that particular element can be explained by some rules. Let us start with those rules. The first one is called as a rule of abundance. What exactly is rule of abundance means? When most of the living organisms are seen, we find that the living organisms are made up of lighter elements at the most. Though the living organisms may find the heavier elements, but their concentration is very low. We put them into ultra trace or even trace elements. But much of the body weight of all these living organisms is made up of the lighter elements whose atomic number is 35 or below 35. So whenever a living organism is made, nature chooses that element which is present in abundant. Right? And also another factor is, suppose if that element is abundant, some salt of that element must be soluble in water at a given physiological pH. Suppose if it is not soluble in water, then though the element is abundant, nature will not choose it. Let us take an example for this. If I choose a biomolecule where zinc is present in a given living organism, such as zinc, in vitro studies, such as zinc, if it is replaced by cobalt, well, the living organism was still found to perform the same catalytic activity in that particular enzyme. It means if that particular organism is grown in cobalt-rich media, what they found is slowly those organisms are trying to develop enzymes where the zinc is replaced by cobalt but without losing its catalytic activity. So we may say that zinc and cobalt are interchangeable. But organisms have chosen zinc selectively. It is simply because zinc is more abundant both in sea as well as Earth's upper crust. So in relation to cobalt, zinc is preferred because of its abundance. We may also take another example. Suppose if I choose some organisms where the protective shell is made up of calcium carbonate, but we don't find the shells made up of strontium carbonate, the simplest reason being calcium has a greater abundance. Getting to the second one, the rule of efficiency. Suppose if there are two elements that are found in abundant, then nature will choose that element which is more efficient. Let us take an example. Flavonoxins and ferredoxins, these are electron carriers. Ferredoxins are more efficient electron carriers than flavonoxins because ferredoxins contain metal at their active site, whereas flavonoxins, these do not contain any metal. This is simply a flavin mononucleotide. So any organism that contains flavonoxins, if at all it is grown in iron-rich conditions, well, what they found is slowly they were switching on to the ferredoxins because ferredoxins are found to be more efficient electron carriers. This is about the rule of efficiency. Then coming to the rule of basic fitness. What exactly is rule of basic fitness? Suppose for the creation of a living organism, what nature found is there are two elements which are in abundant, and these two elements are also inefficient. Both are efficient. In such a case, nature would definitely choose such an element which is abundant, efficient, and which can also perform a particular function. So to enumerate this, let us take a small example of diatoms, which is a form of algae. These can survive by performing a process called as photosynthesis, for which sunlight is required. But to protect that particular species, there is a protective covering, and often this protective covering is not found of calcium carbonate, instead it is found of silica. So though calcium is found in abundant, calcium is also efficient as calcium carbonate in forming a protective shell, but nature has chosen silica for making a protective covering. This is simply because this silica coat could be transparent and it can allow the sunlight so that these diatoms can survive by the process of photosynthesis. Right. Coming to the fourth one, evolutionary improvement of efficiency and specificity. Let me take a small example. Most of us have smartphones where it is fully loaded with the apps, and at every time these apps they get renewed. So just as the apps are getting renewed, in a similar way, even the nature will improve itself. Nature will also refresh itself. Nature will also update itself. And how it is updating? By improving itself, by improving its efficiency and also its specificity. So to explain this, let me take a small example. Copper 1 and copper 2. Let me take a coordination number of 4. For coordination number of 4, copper 1 will form a stable tetrahedral geometry. But if at all we go towards copper 2, for that same coordination number 4, it will prefer a square planar geometry. So what nature has done is, from shifting copper 1 to copper 2, tetrahedral geometry has to jump into square plane, or the reverse process, when square plane has to jump into tetrahedral, this require a higher energy. So the activation energy will be very high. In such a case, what nature has done is, it will not take up a pure tetrahedral geometry. Instead, copper 1, it will always try to form a distorted tetrahedral geometry. So once it is distorted, it can very easily jump into the nearest square planar geometry where the required activation energy is reduced, and this enhances the rates of the reaction. This copper 1, copper 2 switching on could be seen in cryptodioxins. Similar process could also be seen in zinc containing enzymes such as carbonic anhydrase. So such an effect, it was called as entactic effect by Williams. So what is entactic effect means? Suppose if I choose an enzyme, at the active site of an enzyme, it is not having a perfect geometry. Instead, it is having a distorted or a strained geometry which is responsible for its high catalytic activity, which is called as an entactic effect. Well, these are the basics about the biocoordination chemistry. In our next video, we will try to study about the oxygen binding proteins.